Um, yeah, let me think. So I think one thing I want to mention is that no matter is A times B or B times A, the diagonal terms is the same. Okay, so I think that's the only thing I want to mention here. So that's why the trace will equals. Okay. Okay. Then is more spatial matrix. Okay, so the definition 3 tells us the identity matrix here. In identity matrix n by n. So this is a matrix that was ones on the diagonal and zeros on elsewhere. Okay, so it looks like this one. Yeah, so yeah, you look like this one. On the diagonal positions, you will always have 1, and for the rest, they are 0. And if you do the multiplications, then it's not going to have any change. Okay, and you can do it the other way. I mean, from the other order, it doesn't change as well. Okay. Then is the inverse. Okay. So the inverse means that, let's say we have invertible matrix A here. Once it times its inverse matrix, then what you get is the identity matrix. And of course, you can do it this way as well. Okay. Okay. That is the definitions, but how to find the inverse matrix is more difficult. Okay. I think I'm going to cover it later, but for now, you just want to let you know the definition of inverse matrix. Okay. Okay. Any questions? No. Cool. Right. Then we are going to cover the column space, rank, and new space. Okay, so if we have a matrix A here, it's a n by n matrix. The column space of A, which I would denote as like chord of A, okay, it's a subspace spanned by the columns of A. Okay. Okay. Now quickly refresh your memory. So what is the subspace? Okay, in the subspace we have to have like some property, right? So if V is a subspace, then 0 vectors must be contained in subspace. And let's say that V1, V2 is in the subspace. Then the linear combination of it will also in the subspace as well. Okay. Yeah, I think that's it. And of course, you do the multiplication is still in the subspace. Okay. So, right. And the second concept is, I want to refresh your memory a little bit, is the span. Spans mean that now I give you a bunch of vectors, which I denote as A over there. Then you do all the linear combinations among those vectors. And the collections of those linear combinations is the space spanned by those vectors. Okay. Right. Okay. So that's the column space here. What else I want to? Okay, then the next definition, which is rank. So rank is the dimensions of the rank of a matrix A is the dimensions of its row space or column space, which equals the numbers of linearly independent rows or columns of that matrix. So this, so it has several facts here. So the rank should be smaller, or at least equals the minimum, the smaller numbers of its dimensions. And if rank A equals n, and A is an n by n matrix, then we immediately know that A is invertible, which means the A minus 1 is this. Okay, and I want to talk a little bit more about the rank. Okay, where should I start? So I will focus on the column space. Okay. Of course, although here in the definition, you can actually look at the row space as well. But I want to focus on column space. Sorry, give me some time. I think I forgot something here. I think it's important, but yeah. But let me continue first, and if I recall it, and I will talk about it again, right? Right, and then is the new space here. So what is the definition of new space? New space meaning that we want to solve these equations. Ax equals to 0, and what is it look like in the potential? In the solutions here. Okay, which is all the vectors in Rn that can satisfy these equations. And of course, A times X, we can write it as the linear combinations here. And we know that if there's only 0 can satisfy that equations, that means if all the columns in matrix A are linear independent, then the only solution here is 0, right? So the new space is 0. Just one solution, unique solution. And what if the columns here are linear dependent? That means we have infinite solutions of X that can solve these equations, right? So looking at the matrix A, and you can start to think about it like, so if these columns are linear independent, then I immediately know that the new space is 0. Okay, and if it is not, then there must exist some basis in this new space that I can actually use the linear combination of those spaces is going and spend the whole space here. Because let's say that now you find one vectors